Let's take a look at this problem from chapter 16, section 8 of Stokes. We have a line integral that we want to compute, where C is this curve from 0 to 2 pi. Hint, observe that C lines on the surface. So that's a big hint for us, and that's going to probably move us to go from a line integral to a surface integral. So if we were to compute the line integral directly, one of the things that we need to do is find the derivatives of x, y, and z in your parameterization, which isn't so bad. But then when you put in the values for x and y, you'll have a sign of sine t there, and then generally when you have sign of something compositions in your integrals, that gets a little bit more difficult unless there's an easy u substitution that we can take. So instead of doing this line integral, let's think about doing a surface integral. According to Stokes, we have this line integral is actually equal to a flux of the curl of the vector field ds, where S is the surface. So this is our surface S. And it's important to note that if we take a look at this parameterization, this thing looks like a curve in 3 dimensions, but if you look at it from the top view, we got a sine and cosine, and we know that when we switch sine and cosine, we're going to have the orientation going to the clockwise direction. So that means in 3 dimensions, when we're looking at the surface, whatever the surface looks like, our orientation from the top is going in a clockwise direction. So it's going in the clockwise direction, it's going this way. So as it goes around that way, it's going to develop a downward normal vector to the surface. Okay. So let's approach it that way. Well, one of the first things we need is the curl for this vector field. So let's calculate the curl of this vector field. So this is your vector field. Imagine there's a partial with respect to x, with respect to y, and with respect to z on these things. And then if we take the derivative with respect, or if we want to find the first component, then we want to take the derivative of this last component with respect to y, and the derivative of the second component with respect to z. The middle term will be a negative, and then we want the derivative of the last term with respect to x. And then the derivative of the first term with respect to z. And then finally, our last term, we want the derivative of the second term with respect to x. And then the derivative of the first term with respect to y. So simplifying that, we got 2z negative, another negative 3x squared, and then a negative 1. Whoops, negative 1. All right, so that's the first part of this. Our second part of our task is to do this parameterization. Now, if we look at the region that we have, our domain looks like it's a unit circle, so that's great. But we have x's and y's and x's and y's here, so I think I would like to take advantage of a graph parameterization first before jumping straight into the polar parameterization. So recall that the graph parameterization is going to be 2 of the independent variables remaining the same, and then the third one is dependent on the other 2. So if x and y are the independent variables, so z is equal to 2xy. So we'll keep it at that. We've done this several times already. So, but I'll do this again anyway. So derivative with respect to x, derivative of the second with respect to x, and the derivative of the third with respect to x is really the partial of z with respect to x, so that's 2y. And then with respect to y, 0, 1, and 2x. So when we cross them, we can also figure out whether we've got the appropriate parameterization orientation. With respect to x, it's 2y, so that's a derivative with respect to x. With respect to y, it's negative. I'm sorry, this first one is negative. The second one is also negative. So that's 2x. And then the third one is positive 1. So the fact that this is positive 1 means the orientation that we have for this parameterization looks like it's going the opposite that we want. So let's make a note for ourselves that this is orientation reversing parameterization, and then we'll throw a -1 for our answer. So this is what we have. By the way, our domain for this is going to be the unit circle, and dotting this, I think it's easier than dotting this had we changed into polar coordinates right away. So let's see if we can get to our flux. So we got a surface, we got this vector, minus 2z minus 3x squared -1 dotted with minus 2y minus 2x plus 1 dA, and then we'll throw that -1 for our orientation reversing parameterization that we created. So remember, so we probably should change our domain also. So this is not a surface integral now. After taking the dot product, we'll be looking at a double integral over this region. So let's take the dot product and see what we come up with. We'll have a -1 constant outside. We'll keep this as our domain until we officially change into polar coordinates, which we will do. We have a positive 4yz. Oh, by the way, we can't have any z's in there. I forgot to replace this for our z, so let's change that. This should have been, I'll do this in red, this should have been a 2xy, because we want the dA with just x and y variables. So just a quick check, there's no more z variables. So here I essentially have a 4xy times y, and so that's a negative for 8, positive 8 xy squared. So that's that first term. Dot product to get the second term is going to give us a positive 6 x cubed, and then this is a positive -1. And then our dA is dx dy. So now is probably a good time to go to polar coordinates, because we're still hanging on our d over there. So let's change to polar coordinates, and at this point we just change, let's use green again. Our x is equal to r cosine theta, our y is equal to r sine theta, and then our limits go from 0 to 1 for r and 0 to 2 theta, or 0 to 2 pi for theta. So let's keep going. We have r, so that's r squared, and then there's an 8, so -1, double integral 8 r cubed. We have a cosine theta and sine squared theta plus we have 6 and then r cubed cosine cubed theta, and then just a minus 1. And all this gets changed into r dr d theta. So it looks like there's a on our cube that we can factor out, so we can conceivably do this. I don't know if it'll make this any simpler, but we can do this in 2 separate integrals. Oh, by the way, the r limits go from 0 to 1. The theta limits go from 0 to 2 pi. So let's keep going. Minus 1. I'm going to factor out an r cubed. Oh, I can't factor out an r cubed because I'm stuck there without that r cubed. And if we factor out a cosine, unfortunately this is an 8 and this is a 6, so we're not going to be able to combine a sine and cosine. Let's just go through the integral. Let's integrate with respect to r. So the outer integral is 0 to 2 pi for d theta. It's still going to be there. Let's integrate this with respect to r. So this is going to be r to the 4th over 4. Everything else is a constant, so let's have an 8 there. Cosine theta, sine squared theta. And then we have another r to the 4th over 4. We have a 6 there. Cosine 3 theta, which didn't change. And then the antiderivative. Oh, maybe I should have distributed this first. So let's distribute this first. This is r to the 4th. R to the 4th, and this is r. Let's try that again. So the first integral is r to the 5th over 5. Second integral is r to the 5th over 5. With everything else there. And then the last one is just r squared over 2. So we want the r go from 0 to 1, and if you put 0 in for r, it all disappears. So let's see what constants we have left. So we have a minus 1. Let's call this an 8/5. Cosine theta, sine squared theta. And then the second one is a 6/5. Cosine cubed theta. And then a 1/2. And so all that's d theta. So we're just putting 1 in for r, and then we put 0 in for r, then everything disappears. Okay. Now these will take a couple of u substitutions, I believe. So let's go ahead and do that. Let's switch over now with respect to d theta here. Let's do this first one. Let's set u equal to sine theta, and du is equal to positive cosine theta d theta. So that would make this a u squared, and then this will go away with a d theta as du. And then the antiderivative of u squared is u cubed over 3 times 8/5. And now we'll put the sign back in. So it looks like we will have an 8/5. Let's call it 8/15, and then a sine cubed theta. So that's the first one. The second one, we need to break this up into cosine theta and cosine squared theta, which is 1 minus sine squared theta. And if we do that, we'll do the same substitution. U is equal to sine theta, du is equal to cosine theta d theta. So again, that theta d theta combo will go away. And so this is 1 minus u squared. So the antiderivative of 1 is going to be, let's keep the 6/5 here. Antiderivative of 1 is going to be u. and an antiderivative of u squared is going to be u cubed over 3. And then we'll put the sign back in there. So we'll have 6/5 sine theta minus 1/3 sine cubed theta. And then the last one, we have a 1/2 with respect to theta is just going to be 1/2 theta. All right, let's evaluate this from 0 to 2 pi. And if you put 0 in for the sign, these are all signs, so if you put 0 in for the signs, that all disappear. Oh, if you put 2 pi in for the signs, it'll all disappear. So the only non-zero term would be when you put 2 pi in for 1/2. I think I lost this negative sign as well, so let's keep that negative sign here. So this would be a negative, and then a pi over 2 pi divided by 2 is going to give us just pi. Okay, so this is our flux of the curl, or for the same token, it's actually our line integral as well. So we can put pi in there. Let's put pi in there and see if we get the correct answer. Positive pi, I think. Submit answer, and we'll see that hopefully it will be correct. Okay, so that's that problem.